Hello everyone, and welcome to this presentation outlining our recent research about streaming the set cover problem. So I'm going to start by introducing the set cover problem with an example. So this is what a typical problem instance might look like. We have two components here. We have a universe, in this case the letters A through to I, and a set collection which contains sets of elements in the universe. The aim of the problem is to find a minimal subcollection of sets such that every universe element is covered. So in other words, the union over all sets in the solution must equal the universe. And this fundamental problem has many real-world applications, from social network analysis to protein interaction prediction. So it's also useful to define some additional parameters that we will use for analysis later on. So n is the size of the universe, in this case it's 9. M is the size of the set collection, in this case 5. Delta is the size of the maximum set, or the maximum set size, in this case 4, and M is the sum of the set sizes, so the total size of the problem input. In this example, the optimal cover is the set collection S0, S2, and S3, and you can see in the image that together these sets encompass all universe elements. So finding an optimal cover is NP-hard problem, and approximating below a threshold of ln n is also NP-hard. So our primary interest is very large set cover instances. So we have to consider how our algorithm will have access to memory. So generalizing hugely, algorithms have access to two main forms of memory, RAM and external memory. By external here, I just mean external to the processing unit. So for example, disk or access to data over a network. So RAM is very fast, but small. So modern laptops typically have around 16 gigabytes of RAM. Whereas external memory is the opposite. It's slow, but a lot more capacious. So because access to external memory is so slow, this can quickly form a bottleneck if we're accessing arbitrarily. And naturally, if the input fits into RAM, this isn't a problem. Our interest is when this isn't the case. So our interest is when problem instances are much larger than the capacity of RAM. So we can optimize interactions with disk by accessing data in large contiguous chunks. That way fewer queries are required and sequential access is much more efficient. And the extreme of this optimization is streaming access. So this is where we read the whole input sequentially. And again, both direct and streaming access assume direct access to RAM. So these diagrams show the access patterns from the perspective of an algorithm. So each box is a set in these diagrams, and with direct access, the sets can be accessed arbitrarily. So you can see in this example, we're accessing the third set first, followed by the fifth set, followed by the fourth set, and so on. On the other hand, in streaming access, the order is fixed, so we have to access the sets from left to right. In the domain of streaming algorithms, we have one-pass algorithms, or single-pass algorithms, which are only allowed to make one traversal of the stream, and the alternative to that is multi-pass algorithms, which can make multiple passes. So keep these details in mind. We'll see examples of both of these access patterns. So the best known algorithm for set cover is the greedy algorithm, and it's very simple. We start by picking the set with the most uncovered elements, adding it to the solution, and then repeating until the universe is covered. So this algorithm has an approximation factor of big O of ln n, which is essentially optimal. In fact, we can't get below that, or it's NP-hard to get below that. However, the problem with this algorithm is it leaves implementation details unspecified. So most importantly, how do we find the set with the most uncovered elements? And it turns out that this problem is not trivial at all. We can phrase this problem slightly differently by asking, how do we find a set with the highest contribution? So the contribution is just the number of uncovered elements the set contains at the point which it's added to the solution. So one possibility here to solve this problem is to make multiple passes over the input. So at each execution step, we calculate contributions of all of the sets and add the highest one to the solution, repeating until the solution is complete. This has the benefit of accessing memory sequentially, so it's very efficient when working with disk or external memory. However, the time complexity depends on the solution size, and this is clearly inefficient. We're doing one pass for each set added to the solution. So what are the alternatives? An alternative is to maintain a priority queue. So we construct this priority queue which stores the contributions of each set. The set with the highest contribution will then sit at the front of the queue, and we add that set to the solution at each iteration. However, there's a problem. Every time we update the solution, the contributions of other sets might change. So how do we solve that? Well, one way is to use an inverted index. So this inverted index is pre-computed, and it maps universe elements to the sets which contain them. So then when we update the solution with a set from the priority queue, we do a lookup in this inverted index for each element in that set, such that we know all sets whose contributions have changed. We can then update the priority queue entries of these affected sets. And this has a much better time complexity. So in fact, this time complexity can be reduced to big O of capital M, which is linear in the size of the input, if we have a more involved priority queue implementation. However, even as is, it's much improved from the multipass approach. The downsides are it's complicated, and it has this pre-computation step, but most importantly, we've got this inverted index which is doubling the memory access footprint, and our memory access is arbitrary. So this approach really does not scale well to problem instances which are much larger than the capacity of RAM. So what are our alternatives here? Well, disk-friendly greedy is the sort of main practical algorithm for processing large set cover instances. It was described by Cormode, Karloff, and Wirth in 2010, and the main aim of this algorithm is to access memory in large contiguous chunks. So the algorithm takes in an input parameter p, which is at least 1, and controls the granularity of these chunks that we're accessing. So how does it work? As a preprocess, we first write sets to files such that the kth file contains all sets with sizes in the range of inclusive p to the k to p to the k plus 1 exclusive. So each file here corresponds to a chunk on disk, and the smaller our p value, the more files we'll have. So then what we do is we iterate through the files in order of decreasing k, and we add sets to the solution if their contribution is at least p to the k. So remember here that some sets may contain elements that have been covered already, so hence their contribution may be lower than the file's lower set size bound, so p to the k. So to deal with these sets that aren't added to the solution, we reduce them, which means we remove the covered elements, and then we reassign them to the file which corresponds to their new size. And in the final file, we just add sets to the solution if their contribution is non-zero. So that's the algorithm. DFG is essentially a trade-off here. So we're no longer picking the set with the highest contribution at each time step, but rather we're picking a set which is known to have a good enough contribution. And doing this allows us to access memory in a largely sequential manner, which is good for interacting with disk or external memory. The approximation factor is 1 plus p ln n, which is pretty much close to optimal. It's only marginally worse than greedy, and the only reason it's worse is again because we've made this trade-off by not always picking the optimal set. However, this algorithm does have a large pre-computation step, and the footprint is still linear to the input size. So DFG has been shown to perform well in practice. It produces solution sizes very similar to those produced by greedy, and it produces them in a fraction of the time, which is great. And we can even emulate these files in RAM rather than disk, so we can process smaller datasets faster, provided the dataset is small enough to fit in RAM, of course. However, yeah, for problem instances which are larger than RAM, we can't really avoid the interaction with disk, and interaction with disk is always going to be slow. So yeah, ideally disk interaction is something we would like to avoid entirely. So our second alternative to the greedy approach aims to use memory strongly sublinear to the size of the input, so that is strongly sublinear to capital M, big O of capital M. So algorithms which meet this space constraint, described at the top of the slide here, are called semi-streaming algorithms, and the particular algorithm that we look at here was introduced by Emmek and Rosen in 2014. We'll refer to it as the Emmek-Rosen algorithm. So it was originally described in the context of the weighted set cover problem, but we've translated it to our unweighted context. And to meet this semi-streaming space requirement, which is really quite a narrow requirement, the algorithm only stores two values for each element. So we store what's called an effectiveness, which aims to quantify how well the set is currently covered. And we also store an effectiveness identifier, and this is the ID of the set currently designated to covering that element. So how does it work? We start by reading a set from the stream, and then we find the maximal effective subset of this set. So what is that? So a subset is considered effective if all elements in the subset have an effectiveness strictly less than the level of the subset, and the level of the subset is the ceiling of the base 2 logarithm of its size. So I appreciate that's quite a lot of information to hold, so we'll go through an example shortly, but first I'll just go through the rest of the algorithm. So for each element in this effective subset, we set the effectiveness to the level of the subset, and we set the effectiveness identifier to that of the set. So we're essentially saying that element is covered by that set. And we repeat this process until the stream terminates. So one final thing here, instead of returning a cover, we return what Emick and Rosen called a cover certificate. And this is a mapping from universe elements to the sets which cover them. So as I said, this algorithm is really simple to implement especially, but it's quite hard to explain, so I'll run through a quick example now. So on the top we have our problem instance in the form of a set stream. We've received the first set already in this instance, that is set S0. And then on the bottom we have the data structure which the algorithm maintains. So as I said before, we're maintaining an effectiveness which is initialized to -1 for each value, and we're also maintaining an effectiveness identifier, that is EID of X, and that's initialized to a nil value for each element as well. So our first step in the algorithm is to find the maximal effective subset of set S0, and in this case it's actually the whole set. The level of the set is 2, so that is the ceiling of the base 2 logarithm of 4 is 2, and that exceeds the effectiveness values of -1 for each of the elements in a set. So that whole set is effective, and therefore we update the effectiveness and effectiveness identifier values as follows. So the effectiveness values are set to the level of the set, and the effectiveness identifier values are set to the ID of the set, so 0 in this case. So then our second set comes in, and in this case it's a bit different. So our maximum effective subset is only the set containing D. The whole set isn't effective because its level, which is 2, so the ceiling of the base 2 logarithm of 3, which is 2, is not strictly greater than the existing effectiveness values of A and B, which are also 2. Yes, so our maximum effective subset is the set containing D, so we update the data structure respectively, setting the effectiveness to 0, which is the base 2 logarithm of 1, the size of just D, and we update the identifier, of course, to the identifier of the set. So then our third set comes in. In this case, the whole set is effective, so all effectiveness values in this set are less than the level of the set, which is 2. So we update our data structure again, and this time you can see that the identifier of D has been overwritten from 1 to 2, because now it's covered by a more effective subset. Now S3 comes in, and again the whole set is effective because all of the effectiveness values are less than the level of the set, which is 1, so we update the data structure. And finally our last set comes in, S4, and in the set there's no effective subset, so the data structure remains unchanged. Now after this we return our cover certificate, so that's what the highlighted portion of the table is. And we can extract a cover from this cover certificate by simply noting the unique identifiers in the certificate. In this case that's just 0, 2 and 3. Those together are the optimal cover for this problem instance. So this is a one-pass streaming algorithm, and it runs in time linear to the size of the input. It's able to do this with an optimization which we described fully in the proceedings, but it's only possible because we're translating to this unweighted set cover context. It also uses semi-streaming space, which is great, and the key drawback, I suppose, to this algorithm is the approximation factor. So the approximation factor is big O of square root delta. We demonstrate this approximation factor in the proceedings. It's known to be an optimal approximation factor for an algorithm which uses semi-streaming space. However, it's still much weaker than the approximation factors of greedy and greedy-like algorithms, and therefore the question is, how well does the algorithm perform in practice, and specifically, does the weaker approximation factor translate to weaker covers on real-life datasets? So to find out, we prepared C++ implementations of RAM-based DFG and Emick-Rosen. The reason we compare to RAM-based DFG rather than disk-based DFG is just for fairness. So Emick-Rosen is only going to be using RAM, so it would make sense for the DFG algorithm only to use RAM as well. So we formatted in total 6 datasets ranging in size from a few megabytes to 32 gigabytes, and we ran both of these algorithms on each of the datasets on a machine which had 16 gigabytes of RAM. So already you can see the size of the largest dataset is way bigger than the size of RAM. And on each run we measured the solution size, the runtime, and the memory usage. So these are the results for the cover sizes. Firstly, I should mention there's no result for Friendster.dat as the RAM was exceeded by DFG in this instance. We did run disk-based DFG on all of the datasets as well. The results for that are in the proceedings. I won't go into them here, so do take a look if you're curious. So for EMEC-Rosen, the EMEC-Rosen covers are 2% larger in the best case, 18% larger in the worst case, and 8% larger in the geometric average case. And I suppose the key point here really is that those differences are not very significant. So the cover sizes from EMEC-Rosen are only slightly larger than those given by the greedy alternative. In terms of runtime, the improvements are fairly minor, so EMEC-Rosen finds a solution in half the time in the best case, 84% of the time in the worst case, and 72% of the time in the average case. And naturally, in all cases, the disk-based DFG took longer. In terms of peak RAM usage, we have huge savings with EMEC-Rosen. So specifically, EMEC-Rosen uses 73 times less RAM in the best case, 10 times less RAM in the worst case, and keep in mind that's still an improvement of an order of magnitude. So this is a pretty impressive improvement here. And yeah, this reduced memory footprint is really the main selling point of the EMEC-Rosen algorithm. So finally, we measured the solution quality. So these charts compare the contribution distributions of covers from DFG and EMEC-Rosen for one of the datasets. So on the right here, we can clearly see that the EMEC-Rosen cover has more sets which contribute only 1 or 2 elements to the final solution. So we had to think about how we can reduce these. So to better cover these elements at the lower end of the contribution distribution, we can extend the EMEC-Rosen algorithm to make multiple passes over the input. So this is the multipass extension that we came up with. We start by doing a normal EMEC-Rosen pass, and then we restrict the universe based on effectiveness. So what does restricting the universe mean? Well, we reset the effectiveness values of all elements with an effectiveness below a certain threshold. Then, on the next pass, we only consider those restricted elements. And we repeat this process for p passes in total, and after each pass we decrease the threshold. So this is a visual representation of how it works. The diagram shows the universes after each pass. So after the first pass here, you can see the elements in the clear region of the top bar have an effectiveness below a certain threshold, so we reset those effectiveness values to -1. And the elements in the shaded region of the top bar make it to the final cover certificate unchanged. Then on the second pass, we only consider those elements in the clear region of the top bar, and so this sort of recursive approach continues for a total of p passes, restricting the universe, updating the solution, restricting the universe, and so on. And this approach has an approximation factor of big O of delta to the 1 over p plus 1, which is known to be optimal up to constant factors. We give a proof of this approximation factor in the proceedings. So to find out how it performs in practice, we implemented the algorithm in C++. We want to determine whether the cover sizes are reduced in practice. And we also want to compare it to another semi-streaming algorithm. So the one we compare it with is called Progressive Greedy. This was an algorithm described by Chakrabarty and Wirth in 2016. It's a sort of generalization, I guess, of the multipass greedy approach which we described earlier. And it goes roughly as follows. So we, on our first pass, add all sets whose contribution is above a certain threshold, and then we reduce that threshold and repeat for p passes. So it's a very simple multipass algorithm. And this simple multipass algorithm with a clever implementation can obtain an approximation factor of big O of delta to the 1 over p plus 1, so same as our multipass EMEC-Rosen, and Chakrabarty and Wirth show that this is an optimal approximation factor in fact. So how does our algorithm compare to this one? And more importantly, does our algorithm improve the solution quality of covers from the traditional EMEC-Rosen in practice? So these are the results of our comparison. So on the y-axis of both graphs here, we have the solution size, and on the x-axis we have the pass count. The dotted lines in these graphs are progressive greedy, and the dashed lines are multipass Emick-Rosen. We've also included disk-friendly greedy as the solid lines just for reference. So I'm going to quickly flick through these results. We have in total 6 results here, 1 for each dataset. And there are 3 key observations. So first, the multipass Emick-Rosen does indeed improve the solution quality. So you can see in these results that the line or the solution size does decrease as our pass count increases. That is for the dashed multipass line. Second observation here is that given sufficient passes, both algorithms seem to converge to the DFG result, the DFG result is known to perform pretty much very similarly to the greedy approach, so they're essentially all converging to the greedy solution. The third observation here is that the multipass Emick-Rosen converges much faster than progressive greedy in all of the cases. So, in summary, our main result really here is that the Emick-Rosen algorithm works well in practice. This is a really interesting result because, to the best of our knowledge, this is the first competitive algorithm that's just so conceptually different from the state-of-the-art greedy-like algorithms, and we've shown that it's competitive in practice. So, of course, we're working with a trade-off here. The covers produced by Emick-Rosen are slightly larger, but because of that, we have a much smaller memory footprint, and the algorithm runs faster as well. And crucially here, the smaller memory footprint means the algorithm scales much better to very large inputs. So the second note to take in the summary is that solution quality can be improved with multiple passes. So we've described and analysed an extension of Emick-Rosen to multiple passes, and we've shown that it's competitive in practice as well as working well in theory. And that's all I wanted to cover in this presentation, so thank you very much for listening.